I'm waiting. I'm not being charismatic yet. Or ever.
3 seconds.
I still gotta get this
done.
smoke machine.
You're
Is it
live.
happening?
Yes,
We're
you're
live.
live.
All right. All right. Charisma. Here it comes. All right, everybody. Welcome to the general meeting of the Los Angeles Astronomical Society of March 9th, 2026. Are we? What? Okay, we're still going. I will persevere.
Oh, it isn't.
Okay. All right. Thank you all for coming out tonight. We have an excellent speaker. I'm so excited. You guys are going to be riveted gravitationally. Wink, wink. Thanks, Joe. That was pretty weak. All right. We'd like to start every one of these general meetings by outing the new members. Do we have any here in the audience that is the new member? We do. Okay, excellent. I'm coming for you. With love. Acceptance. All right, what is your name?
Hi there, I'm Jerome Ching.
Hi, Jerome. How are you to LAAS?
I was at the Silver Lake Star Party a couple of weeks ago.
Oh, damn.
Yep.
All right.
And then after that, I had to go get a telescope and join up.
Awesome. Thank you. Welcome. Anyone else locally? I don't recognize you two. You're not you? Okay. Okay. Well, you look different now. Good job growing. Okay, let's see. Is there any new folk out in Zoom land that wishes to make themselves known?
I'm new.
All right, Dan. All right, Danielle, what's up?
Hey, nice to meet you all. Yeah, it's kind of a niche hobby, and I was kind of looking for a group to make it a little less niche. So it's cool that I found you guys, and I look forward to meeting you all in person at upcoming events.
Awesome. Where are you? Where do you live?
I live here in LA County. I live in Montebello, so not too far from the Garvey Observatory. I actually live like in northeast Montebello, so just probably about 5 minutes away. So
Oh, excellent.
yeah. No, I'm kind of excited to. I'll probably go this Wednesday too, so maybe I'll see some of you there.
Awesome. Looking forward to it.
Yeah.
Well, thank you and welcome. Welcome.
Thank you.
All right. Is there anyone else? Yes. Applause. Acceptance. All right. Okay. That's awesome. So the remainder of the meeting. Good night, everyone. No. The remainder of the agenda is going to be presenting our speaker, which I'm excited to do. Then I'll have some announcements, including some really, really cool stuff that I'm really excited to share with you all. Then I will bestow the good heavens on a member who I feel deserves it this month. Then we'll give out some door prizes, and then I will tell you the schedule of things to come. So, with just the right amount of ado, I am going to present to you Gabriel Vajente to give us a presentation. Do you want me to really wang it in there for you, or you just want to go for it?
You have the show.
I'm going to do it. I'm doing it.
Go
All right.
You're
He's giving us a
prepared.
presentation on gravitational waves. 10 years of exploring the dark side of the universe. This man is the deputy head of system science and engineering of the LIGO laboratory at Caltech, a national laboratory devoted to the observation of gravitational wave signals from astrophysical objects such as the colliding black holes and neutron stars. Gabriela is a physicist by education and he has worked at the design, construction, and operation of the largest gravitational wave interferometric observatories in the world. He has been working in the LIGO laboratory in various roles for more than 10 years. When he's not working to increase the reach of LIGO observatories, Gabriela likes to spend time running in the mountains or with his own telescope under dark skies in the desert. What's that like? I'm just kidding.
Running at the telescope. You guys have never been up to the telescope?
I have no idea.
No idea,
Never,
right?
never done
Well, I'm
it.
in the wrong place then.
Yeah.
Go home, guys.
Sorry. Yeah. All right. So, yes, let's have a big round of applause for Gabriela.
Okay, well, thank you. It's a pleasure to be here. I've been a member of the... Oh, yes, I have to stand here. I've been a member since 2013, I think. Haven't been very active lately because, you know, life, but it's a pleasure to be back here. So my name is Gabriele Vajente. I am the Deputy Chief Engineer of the LIGO Laboratory. What's that all about? I hope it will be clear at the end of the talk. If not, ask questions and I'll try to rectify all my mistakes during this talk. So tonight I want to tell you a story, and this is a story that starts with a star, like all the good stories. But this star, at some point, as you all know, exhausted all the fuel in the core, collapsed, became a supernova. After that, nothing was there to fight gravity, and this star collapsed and became a black hole. Actually, there were very likely two such stars. So were those two stars already orbiting around each other and then one became supernova and the other one also became supernova? Or were there two stars that became black hole farther away and that capture each other? We don't quite know. What we know is that after a while, those two black holes orbiting around each other kept orbiting and orbiting and orbiting and getting closer and closer and closer and creating deformation of space and time, things that we call gravitational waves. Those gravitational waves were carrying away energy, and so those two black holes, losing energy, they were falling into each other. As they were falling into each other, they were moving faster and faster and faster until they merged and they create one single big black hole. So those gravitational waves, those distortion of space and time, really, you can see them here in this animation. Of course, those are not real images. Those are all simulation animation, what they would look like if you were close by. But you see again those two black holes orbiting around each other. You notice that as they get closer and closer, they move faster and faster because they're falling into each other. But then also, since they're getting faster and faster and closer, the deformation of space and time, those gravitational waves, they get stronger and stronger and stronger until they collide, they merge, they form one single black hole, and there's a burst of energy that is emitted away in the form of gravitational waves. So this is one of the most energetic events out in the universe. The very first collision of two black holes that LIGO detected back in 2015 emitted in about 1/10 of a second the amount of power that this collision emitted in gravitational waves outshined by a factor of 1,000 the entire power emitted in electromagnetic waves by the entire universe. Visible universe, of course. I mean, you understand that. So the amount of energy that goes into this kind of collision is insane. So those are one of the most energetic, the most dramatic events out there. Well, so what are gravitational waves? Well, by now you probably try to figure out where my accent is from. You understand that I'm not, a native American speaker. You can guess where I'm coming from. Some of you know me, so don't give any hints. But often when I don't know or when I didn't used to know the meaning of a word, I go up to the dictionary and try to read the definition. Well, try to read this that I got from a dictionary and tell me if you understand actually anything more than before reading that. I don't, personally. So let's do what you normally do. You have two words, gravitational and waves, so gravity and waves. Let's start with waves. Waves is a simple thing, right? We all understand what waves are. Waves are some sort of periodic oscillation of something that can travel through something, through matter, to space. So sound, now if you're here on the audience, you hear me because with my voice I create waves, pressure waves in the air that carry my voice, sound. If you're online, my voice is converted into electrical waves in a wire and then probably electromagnetic waves bouncing off some satellite and coming down to your computer. We're in California, we know about earthquakes, so that's another kind of waves. So the waves are everywhere, periodic oscillation of stuff. Waves can interfere. So if two waves propagate together, they can go up and down at the same time, so they reinforce each other. Or maybe when one wave goes up, the other goes down, and they always sum up to zero and they cancel out. This is called destructive interference because they sort of destroy each other, right? Remember this interference. It will be important later when we understand how we actually detect gravitational waves. What about gravity? Well, we all thought, and a lot of people before us thought that gravity was a fairly simple thing. Heavy things fall down. Things that are not heavy do not fall down. That's what Aristotle said. Very, profound understanding of what gravity is. Then, Galileo and Newton then understood how to explain how to experiment to understand how gravity works, and then how to explain through mathematics how gravity works. But then we have to get to 1915, this obscure scientist called Albert Einstein, about 110 years ago, gave us what is, as of today, still the best explanation of how gravity works. He told us that gravity isn't quite like a force. It's not that Earth is pulling the moon, but it's more like Earth is deforming space and time. So think of the universe as a big rubber sheet, right? And you put a big ball in the center, you create a deformation. So now if you have a little marble and you toss it on that rubber plane, the marble will go round and round and round. And not because the marble really knows that there is a big ball in the center, or not because the ball is attracting the marble, but because the rubber sheet itself is curved. The same things happen there in three dimensions, very complicated, but with the universe. Earth deforms space and time. The moon is right there. The moon, in some sense, doesn't know that Earth is there. The moon thinks that it's going on a straight line, but a straight line is an orbit just because the universe is curved. The space-time is curved. So that's how gravity works. So now let's put the two things together, and let's go back to our two stars orbiting around each other. So each one of those stars creates a deformation of space and time. Since we have two stars that are moving, they create a dynamical deformation of space and time. And those dynamical deformations are actually ripples in space-time that travel away at the speed of light. Think like you're throwing a stone in a pond and you're sitting on the side of the pond and you look at the waves on the surface. That's how gravitational waves work. Of course, the complicated thing here is that the pond or this rubber sheet or everything, it's two-dimensional. The universe is 4-dimensional if you want to include time. But it's all an analogy. But try to understand the idea here. So the basic idea is that gravitational waves deform space and time. What does mean is that they change the distance between objects. So if this that you see here was a perfect ring of objects out there in the universe, nobody's touching them, nobody's doing anything to them, not pulling, not pushing anything, but the gravitational wave would come perpendicular through the screen, this gravitational wave squeezes the distance in one direction while it stretches the distance in the perpendicular direction. And then since it's a wave, a quarter of a half a period later, the first direction is stretched and the other is squeezed. So things oscillate back and forth that way. So that's the effect of gravitational waves, really stretching and squeezing the space between objects. So this is very big, but now let's go back to those two black holes that collided about 1.2 billion years ago, generating an incredible amount of energy. This energy in the form of gravitational waves spread in a big sphere, wavefront, spherical wavefront through the universe, spread out, traveled for 1.2 billion light years, and eventually crossed Earth. And if we exaggerate a lot the effect, what happens is that these gravitational waves was actually stretching and squeezing Earth. So as they come through, you see something like that. Of course, this is highly exaggerated. Nothing like that really happened. The effect is so small that over a baseline of 4 kilometers, 2.5 miles, the change of distance is so small that to see it, we would have to zoom inside the nucleus of an hydrogen atom, go all the way to the proton, keep going, zooming in. The change of distance is about 1/1000th of the size of a proton. So that's the effect of that gravitational wave crossing Earth. To give you an idea, to measure this effect would be equivalent of monitoring the distance from here to Proxima Centauri and detect a change at that distance, which is about the thickness of a human hair. Okay? I just want to try to explain to you how complicated this thing is. That's why Albert Einstein, back in 1916, when he predicted the existence of gravitational waves, concluded in his seminal paper describing gravitational waves, saying that this is a great, interesting theoretical phenomenon, but the effect is so small that it will be always practically impossible to detect them. Well, I am extremely proud that it took us about 100 years, but we finally proved at least once that Einstein was wrong. The only time so far, almost. So what happened is that those two black holes collided. Those gravitational waves traveled through a big chunk of the universe and crossed Earth on September 15, September 14, sorry, 2015. And what you see here is as passing time in the horizontal axis, those wiggles there is the change of distance monitored by our instrument over 2.5 miles, 4 kilometers. And you can see that the relative change, what we call strain, is in 10 to the minus 21, meaning that the relative fraction, 10 to the minus 2 would be 1%, right? 0.01. 1 part per million would be 0.000001. This is 10 to the minus 21, 0.0000, already lost count, but there are 20 zeros there, and then there's a 1 at the end. So that's the fractional change of distance. It's very small, but you can notice two things. At the beginning, on the left side, there's some noise, background noise of our detector, but then there's this oscillation coming through. And you can notice two things, that the amplitude of the oscillation is getting bigger and bigger and bigger, and also the distance in time between the maxima, the peak, is getting closer, closer, and closer. Because remember those two black holes, they're falling into each other, so they're moving faster, faster, and faster. As they get closer, they also deform space and time more and more. So that's the signature of a gravitational wave. It's what we call a chirp. It's something that sounds like a whoop. That's my best rendition of the collision of two black holes, guys, so be happy with that, okay? So this was the very first detection of a gravitational wave signal back in 2015. Already quite a remarkable achievement, because this proved, among other things, that black holes actually do exist and they behave as predicted by general relativity. They're not only compact objects, but they're really black holes. Proved that binary black holes, two black holes can orbiting around each other and actually collide. This is something that most astrophysicists thought was impossible to have before. And also it was the very first time we detected gravitational waves, the last experimental verification of general relativity. So that was a remarkable result. But the story doesn't end there, of course, because that was 2015, that was 10 years ago. So this is a little, 30-second class on stellar evolution. Well, stars, they form from a cloud of protostars. There are small stars, there are big stars. If any of you is an expert in stellar evolution, please forgive me. I'm going to make it extremely simple. If you have a small star, like the sun, sorry guys, the sun is not a big star by any metric. So eventually, when the hydrogen, the helium, the core is all gone, the sun will become a red giant, there will be a planetary nebula, but the sun eventually will not really explode into anything, nothing fancy, will become a white dwarf and eventually a brown dwarf and just die. Boring. But if the star is a little bit larger, then stuff starts to get interesting. First, because you get a nice supernova, which is always nice to see, but then, depending on how much stuff is left in the core of the star, if this is not too big, let's say up to maybe a couple of times the size of the sun, then this thing will collapse and gravity wins because there's nothing stopping the collapse. And so the electrons are squeezed into the nuclei of the atoms, they merge with the protons, so they generate neutrons. And you end up with a giant ball of neutrons. This is a giant atomic nucleus, right? So something like 1.5 times the size of the sun in about 10 miles radius. That's very dense. Of course, if the star is even heavier than that, then nothing stops the gravity, not even the fact that neutrons don't like to squeeze together, and eventually everything collapses down into what is called a singularity. Singularity is a technical term in physics which means we have no idea what's happening there. So we call it a singularity. So what's happening there, nobody knows. If somebody is telling you that they know, well, they can't, because nobody can go inside a black hole and come out. That's the idea of black hole, right? So if somebody told you they know, don't believe them. But let's go back to the neutron star. I'm digressing here. So neutron star, this big ball of neutrons, the density is so high that a teaspoon is like the weight of Mount Everest, something like that. It's insane to think that you can have something that big. So now let's imagine we have two neutron stars that are orbiting around each other. They're very compact objects, so they will generate gravitational waves too. And this is very exciting because we have a different source of gravitational waves. They're smaller in mass, so they move much, much faster. Then they merge. So right before they merge, those two objects, so two things that are about 1.5 the mass of the sun, are orbiting around each other about 600 times per second. That's fast, right? But then the most interesting thing even is that those are not black holes, they're not black at all. Those are two gigantic balls of neutrons. When they collide, this is a huge nuclear explosion. So detecting gravitational waves from the collision of two neutron stars, not only it's interesting because of the gravitational waves, but it's very interesting because you expect all the aftermath of a gigantic nuclear explosion. Gamma rays, then a big cloud of superheated gas that will emit everything from ultraviolet and cool down and go all the way down. So that's exciting. That's why when in 2017 we detected for the first time the collision of two neutron stars, we were extremely excited that we sent out alerts to all astronomers in the world to try and detect things. But before we get to that, I wanted to let you listen to the gravitational waves coming from the collision of those two neutron stars. So now here normally I stop and say, guys, gravitational waves are not sound, right? They are vibration in space and time. It's very different from sound that is vibration in air. There's no air out in the universe. It just so happens that the frequency of the gravitational waves emitted by black holes and neutron stars, all of that, they are the same frequencies that we can hear. So what I did here in the next slide is take the output of our detectors that are gravitational waves and convert them into sound that we can listen to it, if the sound collaborate. All right, ready to try this? Okay, I'll stop here for a second. Sorry if you couldn't hear me. This depends how the balance goes. But so you see that line that appears there. That's where the gravitational wave signal goes. And you see that as time passes, it's getting brighter and brighter, more intense, and moving up in frequency. This noise that you heard is the background noise of our detectors, like the static in the radio, right? Just before the collision, if you listen carefully, I'm going to play it in a moment, you can hear the whoop of the two neutron stars getting closer and closer and emitting gravitational waves. This is not a simulation. This is an actual signal coming out from the detector. So this is really the sound of two neutron stars that collided about 150 million years ago. Those gravitational waves crosses a relatively small part of the universe, but not too small. And then as they crossed Earth, we could detect them and convert those gravitational waves into sound. No, yes, no, I don't know. So I think that was pretty exciting, as I said, but going back to the main thing here, not only we detect gravitational waves, but we send alert out to the astronomical community, and our estimate is about 1/2 of all astronomers in the world just diverted their telescope, stopped everything they were doing, and tried to see the aftermath of this condition. The SWAP telescope won. It's in Las Campanas. And they saw, as you can see in those two images there, a little dot. So that black round dot is a galaxy, right? And the little dot there was not there in the previous archival image. So that's a new object that is exactly where we told them, go and look there. Then the Hubble Space Telescope jumped in and did several observations. So this is NGC 4993. I doubt any of you knows anything about this galaxy because there's nothing particularly interesting. But you can see in the zoom-in version into that box, as time passes, that spot is getting dimmer and dimmer and dimmer. That's what you expect. After the collision of the two neutron stars, you get a big giant gas cloud that is superheated, and then it goes down, 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 and cools down quicker and quicker. At that point, everybody jumped into the wagon. So we had X-rays and gamma rays, and we had radio waves, ultraviolet, infrared observation, all over the spectrum. And the interesting thing is that the infrared spectrum of the object was changing in real time. So this is real-time astronomy. It's not looking up there, there's something that happened, like the sky never changes. And the interesting thing is that you see exactly what you expect. You start with a spectrum which is extremely blue, very hot gas, and then moves toward red, cooling down, right? Because blue means hot and red means colder. But it's even more interesting than that, because if you're versed in spectrography, you can look at the spectra of the light that was coming out as time was passing, so exploring different areas and layers of this gas as it was cooling down. And you can see a lot of dips and peaks and things that to me and to you maybe don't mean a lot. But if you're an astronomer that look at spectra like that for your living, for your job, every single peak and every single notch there is a signature of a chemical element. And so we proved that in this collision, a lot of the heavy element, heavier than iron, that made us and pretty much everything that we know, a lot of those elements were created in this collision. And this solved a problem that we knew for maybe 20, 30 years, is that, sure, supernovae are a good source of nucleosynthesis. We can generate, well, not we, supernovae can generate heavy elements in their explosions. They're very good at that, but there aren't enough supernovae out there to explain all the heavy elements, the abundance of heavy elements that we see in our local universe. Indeed, neutron stars are the most effective way to produce heavy element. No surprise, you take two balls of neutrons, you smash them together, you generate pretty much everything there. So it's very likely that you and me and everything around us is very much coming from stuff, nucleus and atoms that were created in the collision of two neutron stars, who knows how long ago. So this was another very exciting discovery. So really the beginning of what now we call multi-messenger astronomy. Gravitational waves detected for the first time the collision of those two neutron stars. Because of our gravitational wave observation, we could point in the sky where the two objects collided, and because of that, optical, radio, gamma, every astronomer in the world could jump in and observe that. So I think this was maybe the most exciting discovery in modern astronomy. Other people agreed. That's why the LIGO laboratory and the three founders of the LIGO laboratory were awarded the Nobel Prize in Physics in 2017. Think about it. 2015, first discovery of gravitational waves. 2017, this detection of two neutron stars and Nobel Prize in Physics. That was a pretty fast turnaround time for a Nobel Prize. So we are very proud to be part of the team that started Ray Weiss, that recently passed last year, was one of the founders, the experimental physicists that really had the idea back in the 70s that, yeah, we need to build an instrument to detect gravitational waves, and this is how we're going to do it. And sure, at the time, lasers were only, 10 years old, 15 years old maybe? So it was crazy to think that we would build a laser interferometer to detect something. But he believed in that. And if you go and read the first proposal that he wrote, almost everything was there. Sure, a lot of the details of the technology had to be improved and changed, but he had the vision. So it was really a pleasure to be able to work with him and the other people that are involved in this. So now maybe you have one big question. How do you guys do this? So how can you detect the equivalent of monitoring the distance from here to Proxima Centauri to a few microns or so? Well, we use something, and I hinted at that is called a laser interferometer, which is a complicated word, but what that is an instrument that is very good at measuring changes in distance. So a laser is essentially a source of a light wave, a very precise light wave. So we send this laser beam, this light wave, to a mirror, which is called the beam splitter, that splits the beam in two parts. One travels 4 kilometers, 2.5 miles in one direction. It's reflected back by a mirror. The other half travels to the perpendicular direction, is also reflected back. Now, if you remember what I told you at the beginning, you can tune the two waves so that one goes up and the other goes down, and they cancel out, destructive interference. But now if a gravitational wave comes by, one arm is stretched and the other is squeezed. So the laser that goes on the stretched arm will travel longer and come back later. The other laser will see a shorter distance, will travel a shorter distance and come back earlier. So they don't cancel out anymore. And so some light leaks through. So this is a complicated instrument. Well, it looks very simple here, right? It's an instrument to convert changes in the distance due to gravitational waves into light. Seems like a fairly straightforward idea. It turns out that if you start doing the math and design this thing, you discover that if you want to be sensitive enough to gravitational waves, and you say, let's make it reasonable, we make it 4 kilometers long, which some people would say it's already unreasonable, but let's do it. We use the most powerful laser we have available at the time. What you get is an instrument which is about 1,000 times less sensitive than what you need. So you're missing your target by a factor of 1,000. So what do? Well, you could make it 1,000 times longer, right? Very easy. There's a lot of flat space out there. Of course, in the over 4 kilometers, the curvature of Earth, I assume that we all agree that this is not a correct picture of the reality of the planet. Even over 4 kilometers, the curvature of Earth means that the center is about half a meter or something like that. That we have to dig. Over 4,000 kilometers, besides the fact, where would you build something 4,000 kilometers long? Not reasonable, right? Well, then maybe you can increase the power of your laser. Yeah, we don't have that super high laser powers yet. So the idea of brute forcing to a better instrument doesn't quite work. So unfortunately, we had to be smart, which is always harder. And so the simple instruments start to become a little bit complicated. And I'd like to say that this is a very, very simplified scheme of our instrument is. But you can recognize there's a laser, there's a beam splitter, and there's two, not up to scale, but two 4 kilometers long arms. And you recognize the basics of what is called an interferometer. Then what we do is we add some mirrors at the beginning of the 4 kilometers long arm so that the photons are bouncing back and forth about 300 times. So basically, you make those arms 300 times longer. You paid out with a lot of complication, but no, the idea is good. Then if your interferometer is tuned to have destructive interference, means that you send all the laser in, there's no laser going out, almost no laser going out anywhere, everything is reflected back by the end, so all your laser power is coming back into your face. Well, in the face of the laser, but it's never recommended to put your face in the laser, by the way. So what do? You add right after the laser another mirror, which is called power recycling mirror, because it literally recycles the power that otherwise will be wasted. And so effectively you increase the power of your laser. So this is just a very quick explanation to try to tell you that to get to the sensitivity that we need with LIGO, we had to start with the basic idea, which is good, but implement a lot of tricks to try to get where we needed. So here I would like to take you all and show you our observatories, but we can't just jump on a plane now and fly to Louisiana or fly to Washington State. The other second best thing I can do is show you a video. So here we are flying over the central area of our detector, the LIGO detector, Hanford is called, in eastern Washington State. So you see it's very dry and desert out there. So now we're going to switch to the one in Louisiana, which is a lot more greenery. So the laser and the beam splitter is in that building, and then you see the 4 kilometers concrete pipe going one direction, and you saw the other one going in the other direction. Now we're back into the one Washington. This is an animation of what it would look like if you were flying into the concrete pipe, and then inside that concrete pipe there's a steel pipe, 4 kilometers long, completely sealed because we pump all the air out. And this is how things look like into our central building. So see those big tanks are all vacuum tanks. Our mirrors are suspended into that system. And the reason that we have this complicated system and vacuum, etc., is that our mirrors and the laser need to be in vacuum, because otherwise vibration due to air would give us a lot of noise. I kind of mentioned in passing that we have two detectors, one in eastern Washington State and one in Louisiana. Why? Well, each one of our detector, fortunately or unfortunately, depending how you look at it, is omnidirectional, meaning that it can detect gravitational waves coming essentially from any direction in the sky, which is great, because could you imagine how you could point a 4x4 thing? That would be impractical. But it also means that with only one detector, there's no way you can tell where a signal is coming from in the sky. So we need two, far away, and so we can do a triangulation, doing exactly what your brain is doing right now with your ears. So if I put you to sleep and your eyes are closing, you can still tell that my voice is coming more or less from the center, or more from the left, or more from the right, because the brain is able to measure the tiny difference in the time of arrival of my voice to your two ears, and by that triangulate the direction. So we do the same. We measure the few milliseconds of different time of arrival of the gravitational wave signal at the two detectors, and with that we can point to the sky. 3 would be better. That's why we collaborate with a similar detector in Europe called Virgo, which is not quite as sensitive as we are, but still useful to help with the localization in the sky. I gave you some ideas of the kind of technologies that are involved in LIGO. There's a lot more, of course. I already mentioned how everything needs to be in vacuum to avoid vibration due to air and sound, to avoid contamination. You see the people there, they are dressed up in something that looks like an hazmat suit. But when you see in the movie the people coming in with a hazmat suit, it's to protect them from any pathogen or stuff outside. We dress like that when we work in our instrument to protect the instrument from the dirtiest thing there, humans. And because if you touch anything with your hands, the grease will, in vacuum, will take ages, really years to evaporate. That's why everything needs to be properly cleaned and baked so that everything evaporates. Our mirrors, they are gigantic pieces of glass. They are like 34 centimeters in diameter. What is that? 16 inches, more than that, 18 inches maybe. 20 centimeters, 8 inches thick. They're 40 kilograms, 90 pounds maybe, of ultra pure glass. The surface is polished to the equivalent of a lambda over 30,000 in astronomical parlance, meaning that we have to hit exactly the figure that we need to within 0.1 to 0.3 nanometers. So few atomic layers. Of course, the ground is always shaking because of micro-earthquake and traffic and stuff. So we can't have the mirror just sitting on ground, because they would move about a million times more than what we're trying to measure. That's why we need to suspend them into multiple pendulums, because each pendulum will reduce the motion of whatever is suspended from the suspension point. We do have multiple passive and active isolation systems that continuously measure the motion of the ground, and counteract that. So there's a lot of complicated technologies going in. Nevertheless, LIGO is a very successful experiment. So I talked about two events, the very first gravitational waves ever from the collision of two black holes and the collision of two neutron stars. By the 10 years since the beginning of the gravitational wave astronomy era, LIGO has detected a lot more, 400 plus signals from the collision of different black holes, neutron stars, etc. Here you see, as passing time, couple of dots connected by arrows. So you see two dots that then merge into a bigger object. If it's blue, that was very likely a black hole. If it's orange, it's very likely a neutron star. So you see some neutron stars that merge into something that's probably a black hole. And there's a lot. We have 218 events in the first 4 observing run. So the way we work, right, we design the instrument, we build it, we turn it on, it doesn't work. Because the first time you build something this complex, right? So it's hopeless to think that it's going to work right away. Imagine whoever built the very first car engine. Do you think that they built the very first car engine, they turned the key, or the equivalent, and the thing was just going? No, right? So same thing here. You turn on your instrument, doesn't work. You do what we call commissioning. You make it work. Then at some point you get a good enough sensitivity, you reach far enough in the universe, you say, okay guys, stop tinkering with your instrument, stop tinkering with your car, let's go for a ride now, right? So you start observing the universe. And so we do what is called an observing run. And with a lot of fantasy, we call them observing run 1, O1, O2, O3, O4. And then maybe we have O3A, O3B, O4A, O4B. Yeah, we're scientists, right? No, we're not necessarily the most creative people in terms of naming. But as we were getting farther and farther in those observing RAM, we were improving the sensitivity of our detector, reaching farther and farther away in the universe and see more and more events. And now we have 218 in the first 4 catalogs that we have released, and we have about 173 events in the last part of the last round that are still preliminary, will be confirmed in the coming years. Now we are stopped and we are installing a lot of upgrades, hoping to come back sometimes in October or November with an even improved detector, take another 6 months of data, and then improve further and keep going at that for a while. So this is the present of gravitational waves. What about the future? Well, we have plans in the next 3 to 4 years to get to the limit of what we can do with our detectors right now, which is almost doubling the range in the universe that we can detect stuff. If you double the distance in the universe, it means that the volume is about 8 times bigger. So now we are detecting something of the order of 1 gravitational wave event every 3 days. So we will, at that point, get to have 2, 3, maybe 4 events a day routinely, every single day. That's a lot of gravitational wave signals. What are we expecting? More of the same, more black holes, more neutron stars. Oh, I should have mentioned that after that we have plans for future upgrades of the detector. We have something which is called Cosmic Explorer. The idea is if 4 kilometers works fine for you, why don't we make bigger? Why don't we make it 40 kilometers? So that's a huge instrument, and we plan to be building that in the late 2030s probably. Maybe I retire before that, who knows? And, but that is called Cosmic Explorer because it will be so sensitive that it will detect every single collision of neutron stars or black holes in the universe. Because it will be able to go so far out in the universe, which means so far back that we don't expect to see any black holes or any neutron stars just because there weren't stars yet that far in the past. So if we see collision of black holes that far, those would be primordial black holes that were generated during the Big Bang. We don't know if those exist. That would be interesting to know. So we expect more of the same. We know that there are other signals, other sources of gravitational waves to detect. For example, pulsars, neutron stars that spin very quickly. If they have a mountain which is about 1 millimeter in size, again, 10 miles, right? In the radius is 1 millimeter is the maximum size of a mountain you can have a neutron star because before the thing rips apart because of tides, right? So if you have something like that, this is a spinning thing that will generate gravitational waves. We haven't quite observed them, but we hope to see them fairly soon. The explosion of supernova will generate gravitational waves too. We haven't seen that. Hopefully it's coming. The Big Bang itself, the big explosion of the mole, should have generated gravitational waves. It's very uncertain how big the gravitational waves are. And the reason is that now we can observe up to about 300,000 years after the Big Bang using electromagnetic radiation. Because before that, the universe was opaque to electromagnetic radiation. So you have to extrapolate back 300,000 years to know what happens during the inflationary period. A de-inflationary period is when gravitational waves will be emitted. So that's very uncertain, but that will be exciting. Hopefully, Cosmic Explorer and those detectors in the coming decades will be able to detect that. Finally, hints of what dark matter is. At the end of the day, we need dark matter because of its gravity. And hey, we're detecting gravitational waves. Quantum gravity, this holy grail of modern physics, how to put together gravity and quantum mechanics, we don't know. But at the end of the day, gravitational waves might very well be the way to discover that. And then there's always the unexpected. The best discoveries in physics are always coming from things we did not expect. With that, I hope I explained you enough of what I do and why gravitational waves are interesting. I'm going to leave you with a few contact information here. And actually, I'm going to go to these. There are some QR codes that you can scan if you want. And find me on LinkedIn, find the LIGO laboratory website. There's a lot of video and documentaries that will explain things way better than I did. And also, we are on Instagram, not very active recently, but you can follow us and get some more news. That's what I got, guys.
Thank you so much. That's amazing. All right, so now for the Q&A portion of it. Yeah, here's some hands. All right, here we go.
Okay.
Joe first.
Gabriel, can you tell us something about the new mirrors that you helped develop and if
Yeah.
they've been installed already or when they might be?
Yeah, so I told you that our mirrors are made of glass, right? But glass is transparent. You have to make it into actual mirrors. So astronomical mirrors, they have typically aluminum or gold or silver on top. That wouldn't cut it for us because you can get maybe 97, 99% reflectivity with that kind of materials. Oh, maybe I should.
Oh, you want the,
I should.
I can go back.
Should be here, right? So what we want is 99.9995% reflectivity, right? So to do that, you have to put different kind of glasses, thin layers of different glasses on the surface, what is called a Bragg reflector, alternating different glasses. Unfortunately, it turns out that those materials are fairly good optically, but from the mechanical point of view, they're not great. They vibrate too much. And so we need to change some of those materials, find new materials to try and have coatings on the mirrors that vibrate much less. So this is one of the research and development that I've been involved since 2017, I guess. And we recently have a very good result, a very good candidate. So we are going to produce new mirrors probably in the coming year, and then test them out and hopefully see an improvement.
Awesome. All right, who else here in house? Bobby. This is my lot of life.
I gotta get some steps in. I've been a big fan of your work. I've been looking forward to the expansion of facilities and everything like that since I saw you guys at the Pasadena Convention Center earlier this year. I was just curious, how can you tell if it was black holes colliding versus neutron stars? How are you able to differentiate? Like, what kind of reference data do you have?
That's an excellent question, thank you. So the bigger the object is, the slower it moves. So when you have two black holes, the bigger the mass and the slower they orbit around each other. Think about it if you want. If they are more massive, they're also bigger in dimension. And so they cannot go too fast, because to go very fast, they need to be very close, but they're so close that they touch and they merge. So the higher the frequency of the gravitational wave signal, the smaller the mass. So by just looking at the waveform of the signal, what is the peak frequency, what is the frequency evolution, you can tell what is the mass of the two black holes. So if the mass is below 2 solar masses, then that's very likely to be a neutron star. If it's above 5 solar masses, then it's almost certainly a black hole, because you know that nothing can sustain gravitational collapse above 5 solar masses. Things in between is what is called the mass gap. There isn't supposed to be anything there. So if we see something there, it's going to be a mysterious object. But that's how we can tell the size of the objects.
Let's take one from Zoom land while I work the microphone up to the thing. Who do we got out there, Spencer?
There's one that says, let's see, what's the current staff of the LIGO project?
So the LIGO laboratory is a national laboratory, so we have 4 main locations. One observatory in eastern Washington State, one observatory in Louisiana, the main science and engineering team at Caltech, and a science and engineering team at MIT. Totally, we are about 200 people. And that includes scientists, physicists, engineer, mechanical engineer, electrical engineer, civil engineer, vacuum engineer, computer scientist, administrative people, all of the above, because you need everything to run such a big team, such a big experiment.
I have 2 questions. Number one, age-old astronomical question: how do you differentiate between something that's really big and something that's just close, assuming that gravitational waves decrease with the square of distance like regular waves? And then second question, how much mass is lost in one of these mergers?
Thank you. Great question. So for the first one, the interesting thing is that in gravitational waves, mass tells you everything. So once you see the frequency evolution of the signal, you know the mass. But once you know the masses, you know how intense the gravitational wave that is emitted should be. So gravitational waves are self-calibrating, if you want. You don't need a different way to tell how far it is. Then what we measure, lucky for us, is the amplitude of the gravitational wave. So that goes down with the distance, not the distance square. So once you know the masses, you know how much energy is emitted at the source. You see how much you got here, and then you do the computation. That's as simple as that. In terms of masses, in the collision of the very first two black holes that we detected back in 2015. It was about 30 and 30 solar masses. When they collided, we lost about 3 times the mass of the sun in energy. So that's literally 3 times the mass of the sun was converted from mass to pure energy. That's a lot.
Enough to shake the universe, right?
Yeah, pretty much. Quite literally.
All right, what else do we have from Zoom? I saw Shane had a question.
Yeah, how long does it take to vacuum out a 4 kilometer tube? And do they always kept under vacuum or is it cycled?
Yeah, so the 4 kilometers pipes are, we pumped the air out once back in 1999, and they have never seen air ever again. They always kept in vacuum. We do that by having big gate valves that can section off the 4 kilometers at the beginning of the end. And the reason is that it took us something like 6 months to pump all that air out, because it's not enough to pump the air out, which is already pretty hard. But metal, like everything, absorb a lot of stuff in the surface. So the metal will absorb a lot of hydrogen and water and stuff from the atmosphere. And that slowly evaporates over time. So to make that quicker, we have to wrap the whole thing into a heater, like a heated blanket if you want, heat it up to, I think, 100 C or something like that, or more than that, for several months while we were pumping the air out. That was a very long and expensive process, and so we don't want to repeat that ever again. That's why the tube never saw air.
Was there another one on Zoom? I think I saw
Yes,
one.
is there any concern with nuclear storage affecting this research? If so, what's needed to protect it?
I did not catch that, sorry. Can you read again?
So the question is there any concern with the nuclear storage affecting this research? And what's needed to be done to
okay.
protect it?
So maybe the question, and correct me if I'm wrong, is that the observatory we have in Washington State is in the Hanford Nuclear Reservation, where part of the Manhattan Project, and now they store a lot of nuclear waste there. But that doesn't have any effect on what we do because we are not doing anything that is affected by radiation. Well, except the humans, but the safety is pretty good there, and so there hasn't been any problem so far. A couple of scares of sheltering places, but that turned out to be nothing, so that's normal. Sort of normal.
You mentioned that you're able to send out events to astronomers. Do you have, how much advance notice do you have of events when they happen, or is it something you can only identify once they happen in real time?
So, great question, thank you. So for black holes, the duration of the signal is a fraction of a second. So there's no advance notice. Also, gravitational waves travel at the speed of light, so they won't come here any earlier or later than any electromagnetic radiation. So there's no early warning for that. Neutron stars, instead, the signals now can stay a couple of minutes into our observing band. So we could be able to send an alert to telescopes maybe with a minute of advance notice. Practically, we were not able to do that, and we managed to send out an alert a few minutes after we actually detected gravitational waves. So we have not catched really the prompt optical or electromagnetic emission, but the Fermi satellite that was in what is still in orbit around Earth saw the prompt gamma ray emission, because like us, Fermi is almost omnidirectional, so it's observing the big fraction of the sky. So we saw the prompt gamma ray emission, and then we sent out an alert within a few minutes, and then it took 10 hours for the telescopes to find it, because they had to wait, the telescopes that were available had to wait for the sun to set and that thing to rise. And also, the area in the sky that we give them is not only one single galaxy, it's fairly big, so they have to really go and map multiple galaxies and see where, if in any of those galaxies there's a new dot.
Anything else out on Zoom?
Yeah, there are 2 questions. What's the next phenomenon that you want to detect but cannot yet based on current technology?
So what is the next signal, next event we want to detect? Yes, this is what I mentioned a little bit here, right? In my personal opinion, the most interesting thing is being able to detect collision of black holes with higher and higher precision, because that's where I think we will see signature of quantum gravity. Because think, how did we learn quantum mechanics? How did we learn how elementary particles, subatomic particles behave? We built particle accelerator. We take a proton, we take another proton, we accelerate, we make them smash, and we see what comes out. Well, that's exactly what we're doing here, except that we cannot make our own black holes, luckily. We cannot make our own black holes, but the universe is making a lot of black holes, it's smashing them together. So really my hope is that the next thing that we will discover, hopefully soon, is that two black holes, when they collide, they don't quite follow the prediction of general relativity, of classical mechanics, but there's some deviation there, and that will be a signature of quantum gravity.
What was the other one, Spencer?
So how do you transmit data from the LIGO laboratory? Where's the main processing computer?
Yeah, so to give you an idea, each one of the detector produce, if I'm not mistaken, about 80 megabytes per second, which, to give you, I used to tell people how many DVD that is, but nobody knows DVD anymore. So that's like if you were streaming 100 high-quality Netflix movies, okay? So that's the amount of data that LIGO produces, each one of the detectors. So that's stored locally and then is sent in basically real time with 2 or 3 second latency to several computing centers. One is at Caltech, one is at Northwestern University, and another couple of them are in Europe and around the world. So the main analysis in close to real time happens at Caltech, and then alerts are generated here and sent out.
I saw one from Tim
Yeah.
in there.
Yeah. Will LIGO ever detect gravitational waves from the Big Bang?
So the current detectors we have now, LIGOs, are not sensitive enough to detect gravitational waves from the Big Bang. We hope that with the future iteration, very likely Cosmic Explorer, so in the next 20 years or so, they will be sensitive enough to see what's coming from the Big Bang. What's interesting is that those would be gravitational waves coming directly from the inflationary period, so directly, basically right after the Big Bang. But as you can imagine, prediction of how strong those gravitational waves are very uncertain because we have no other way of seeing what's happening there. So detecting that would be the holy grail of modern cosmology, essentially, being able to observe the inflationary period directly.
Awesome. I guess I have one myself. So with what you guys are doing, it's understood that the beams themselves aren't affected by gravitational waves because it's not compensating by the stretch. Is that photons are not affected by gravitational waves?
No, everything is affected by gravitational waves, but light always travels at the speed of light, no matter what happens, right? Meaning that even though the wavelength of the laser is squeezed and stretched, it's always traveling at the speed of light. So if the distance gets closer, that beam will still travel at the speed of light and travel a smaller distance at the speed of light. So the fact that the speed of light is a constant is the trick here.
Even though the universe is changing shape.
The universe is changing shape, but light will always travel through whatever shape at the speed of
almost
light.
Extra universally in a way like that.
Well, it's one of the tricky things, but the light, no matter the shape of the universe, of how much you stretch or squeeze space-time, light will always travel at the same speed. Why?
The shape of the container.
Hey, this is how the universe works. I didn't design it.
No, good job if you did. I don't know. No judgment from me. Any questions from anyone else here? Oh, we got one. All right. I'm going to go for a reach, and we got one up there too. All right.
I'm sorry, there's one more question on Zoom.
We got a local one too. But
Okay.
Okay. Well, thank you for an excellent presentation. And I was wondering if you have any kind of estimation of how often you will be detecting black holes or neutron stars spinning and collapsing on each other, given the size of the universe, and how far away would this event occur that it isn't big enough that you can see it. So
Yeah, so at the current sensitivity of the detector right now, we have a gravitational wave signal, mostly from the collision of black holes, once every 3 days. Now, we plan in the next, say, 4 years to double the range of our detector. That means 8 times more detection, so let's call that 3 detection per day, right? We have plans then in the next decade to double that again. So that means like 6, 7 detection per day. Finally, Cosmic Explorer would be, roughly speaking, 10 times more sensitive than that. So we are going to the point where we'll have multiple detection every hour. So this is really freaking out my colleagues that are working on data analysis, because at that point you have to solve a lot of problems like how do we process all that information? What happens when 3 or 4 signals are one on top of each other? And I look at them and say, well, my job is to make your life harder by making this detector better. So you figure it out. But it's going to be very exciting, because then at that point you'll have so much data that you can only analyze it on a statistical level. And you can do a lot of statistical analysis with that.
Is there, it seems like this would be right for being a space telescope, so that you don't have to worry about vacuum and all that stuff.
Yeah, so there is a project called LISA, the Laser Interferometer Space Antenna. I don't work directly with that. It's a collaboration on NASA and ESA. So they are scheduled to launch in the 2030s. And that will be a 1 million kilometer triangular interferometer. Of course, at that point, the technology is a little bit different. You cannot have 1 million kilometer long vacuum pipes. But as you said, space is already fairly empty. But you have other problems like micrometeors, solar wind, all of that. Also, you can't fly a 1 million kilometer triangular formation in solar orbit, of course, because there's no space around Earth for anything. So that will be a formation flight that will not maintain the exact distances. So there's a lot of complications. But being this big, it will be sensitive to very low frequency, which means very big objects. So if we can observe now up to maybe black holes that are as big as a few hundred times the mass of our sun, that will look at supermassive black holes, the stuff at the center of galaxies. So that will be a complementary science. Like, you know, after all, having been doing optical astronomy for centuries, you finally have a radio telescope. Same electromagnetic spectrum, sure, same sources, more or less, but different information.
It'll be like your subwoofer.
Yeah, exactly, a very big subwoofer.
What was the other one I saw on Zoom?
So how do you distinguish noise signals from what might be potentially artificially generated gravitational waves?
So that's one of the reasons we have 2 detectors, right? So if there's some local disturbance, like a local earthquake, a glitch in the power line, somebody yelling too loudly, or somebody jumping around, or traffic. So one detector is in Washington State, the other one is in Louisiana. Local disturbances are very much uncorrelated. So we always require correlation or coherence between the signals of the 2 detectors. And that takes away all the local disturbances. So it's extremely difficult to imagine of any global event, because earthquake, sure, but then the seismic waves travel much slower than the speed of light. So the earthquake will hit the 2 detectors at much different frequencies and time. So having 2 detectors and asking for coincidences is a key factor for getting rid of all spurious signals.
Anybody else here?
I got one more.
All right.
Are they still working on the detector in India?
Yes. So we are going to build finally a 3rd LIGO detector in India. We have civil construction on the infrastructure should start as you speak. So they have acquired the land, and the contract has been signed with a local construction company. So we expect in the next 5-6 years we will have a LIGO detector in India. That will be useful, because India is sort of almost the other side of Earth, so that will help a lot.
And then you can really triangulate them.
Yeah, yeah. We would have loved to have that in Australia, because it's literally on the other side of the planet, and there's a lot of empty space there, but we couldn't convince them to have a detector. So.
Anybody else on Zoom?
Yeah, there's one. What will be the improvement in detection with India?
Yeah, so having an additional detector means that we can triangulate much better. So instead of telling the astronomers, hey, our signal comes from this patch in the sky, which is 20 square degrees, which is huge for optical telescope, we can tell them, hey, it's coming from this patch in the sky, which is 1 square degree. Now, with the Vera Rubin telescope now online, this is almost not relevant because the Vera Rubin has such an incredible field of view that they can basically map the entire sky in a couple of nights or something like that. So we could give them several 10 square degrees in the sky and they could map it out right away. And we have agreement with them that if there is an interesting candidate, they will drop everything they're doing and just map that area of the sky.
As long as it's in the southern hemisphere.
Yeah, well, of course. For us, it doesn't really matter because the gravitational waves go through Earth, so we don't care. But for them, those optical telescopes, they want the sun down, they want to be above horizon. So many requirements, guys.
Through the center of the Earth, whatever.
Yeah.
Just limited over here. All right, do we have anything else anywhere?
That's it on Zoom.
All right, everyone is appetites are sated. Well, thank you very much. That was awesome.
Thank you, thank you.
It's always such a crazy thing for me after getting like a lecture and a Q&A like that. I'm like, okay, now let's talk about our club. We're cool too, okay, Gabriella? Sheesh. All right, some announcements. There has been, as you all know, this is our centennial this year, and part of what we've been working on. Yes, celebrate us. Like all of us, all the way back to antiquity. And as part of that, we have a lot of stuff coming up. I'll have Laura May comment on that in a little bit. But in the shorter term, we have commemorative merchandise that you can participate in owning. Much like the hats started first. Let's see if I remember to do this. This is going to be not Zoom. Oh, it's going to be this because he unplugged it. Let's see, how do we get the stage computer over there again? Which one is it? Oh, that one right there. The one that says exactly what I asked it to do. Brilliant. You guys are hired. Okay, we have a whole slew of new merchandise on the web store. In the past, we've had, it's been our traditional logos with the regular fare. We've revamped it all as of today. So you'll note that there's a lot of stuff on here that's really expensive, but this is all fundraiser stuff for the club. This is all going to go into the general fund that we'll be using for all manners of stuff. Some of it will make it to Lockwood. Some of it will be used for Garvey. But we have all kinds of stuff up here. We have vests. We have jackets. We are trying to eschew the aesthetic of only a certain thing, like when we were first talking about putting new things on here, it was only stuff that I would want to buy, and then we realized that shouldn't be how it is. Everybody has their own thing. So I implore you to go up there and check out all the different things, and then beyond that, we started incorporating more of the worm logo stuff on there too. Now this isn't replacing anything that we had. There's still plenty of traditional stuff too. The regular worm logo stuff is more of a regular price because it's not necessarily direct fundraising, but we have all manners of stuff, including the hoodie I'm wearing right now. And then we got all that, and then we have plenty of traditional LAS stuff with the logo that you know and love. So, if you feel like getting a fresh up to your wardrobe or for your whatever you're using to hold your coffee or to stay warm, I recommend you check it out.
What about cargo shorts?
Sorry, cargo shorts are a very personal matter. They should all be crafted by yourself in your basement. I did bring the hoodie that I bought, the beanie that I bought. You can check it out. And this is actually a prototype hoodie for this. We're going to change it up a little bit, but I am actually going to leave this here as a door prize. So you might want to win. It's pre-warmed. It's really warm by me. I've been working on this for hours. So if you're remotely cold, this is it. I am your, yeah, my ghost is your door prize. Is how this works.
Your hat, Keith?
Okay.
Give us your hat too.
Actually, these are for sale. So we have 2 more of these left, but I know everyone's like, oh, but Keith, I want the LED hats. I'm like, I know, you gotta wait. Hot damn, it's gonna happen. I got new ones. So look for the LED hats coming up definitely by April Fool's Day, and I'll be serious about the fact that they're available, maybe. But yeah, there's more. There's going to be more Centennial hats like this, except with the red lights and the white lights built into them. I'm supposed to be getting the blanks in about a week or so, and then I'll send them to the embroiderer, and then I'll put a big blast out that they're going to be there. Other worth noting, I didn't even realize this, and all of the stuff on the website, merch-wise, they all have a bunch of different colors in there. It isn't all just black and white, so we did the best we could to actually, like, whenever there were alternate colors, that you can see them. But if you wish, I wish that was in black, check it out, it probably is. Or if you wish it was in blue, sometimes maybe it will be. So it's worth your time to investigate that. In this moment, I would like to introduce our Vice President, Laura May Abron, to speak about our Centennial celebration.
Hi,
Are you there, Laura?
everyone. Yes, can you hear me?
Let's zoom the.
Can you hear me?
We should still be able to hear. Let's see.
Yes? No?
Okay. All right.
Travis, you can hear me.
Yeah, we got you.
Good on Zoom.
Okay, cool.
Yeah.
So the form went out just a couple of days ago regarding our big Centennial Star Party from April 25th. I'm happy to announce, at almost 60 telescopes out of 100 that we are trying to get on the lawn. So I know, it's very, very exciting. I think almost everything. So the proposal has been submitted a while back to Dr. Krupp and Mark Pine, the directors of Griffith Observatory. So almost everything is good to go, but we need your scopes. And so I want to encourage you, and I hear some of the new people who are here tonight or who are here on Zoom say, "Ooh, I have a brand new fresh telescope." So this is your chance. Come show it off. Come bring it to the party. And please sign up. This is going to be really cool. We're doing some special things right now. We're having discussions about, well, I don't want to reveal everything, but printing little things for the people who will bring telescopes. And if one clarification for the form, which I will talk a little more about, I'm trying to do a prize for something kind of unique. Maybe for anyone who knows Stellafane a little bit, they have all sorts of insane telescopes over there. But I really want to encourage you to grow the numbers. And for example, I'll be bringing a little toy telescope from a Smithsonian magazine that someone gifted me years ago, as well as a little homemade spectroscope. So if you've got a little toy telescope or things like that, don't hesitate, bring them. We want all manners and types of telescopes. This is part of the fun. So please sign up, and that way we can sort all this out and figure out how to get everyone in the parking lot and not make the managers of Griffith Observatory too angry, the directors. So I hope you'll sign up, and I hope you'll join us April 25th.
Awesome. I know that Gabriella's got a pocket interferometer lying around somewhere. He can
bring all of LIGO.
We got 2 laser pointers, man. We can make this happen.
That'd be great.
Okay, and a splitter, and that's right. There's only one and a couple of mirrors. We can hook you up. I know a guy.
Thank you, Gabriele, for the great talk again.
Yeah, amazing. That's true. Well, if we had, let's say we had 400 green lasers that we put together, would that help you guys out at all?
People after that.
We may have 400 green lasers. I wish it wasn't funny. Okay. All right. Other things to mention, as per always, if you're excited about something that happened to you, be it the eclipse or that time that you put a green laser together and created an interferometer in your house, or an otherwise cool astronomical experience, talk about it to the club. Write something about it to the bulletin. Talk to Michael at bulletin@laas.org, or if you are slightly lazier than that, just send it to our club's Instagram. Just DM la.astronomical society dot nothing. That's just la.astronomical society, and then it'll get put up there. Ed's always looking for stuff, as is our bulletin. Now is where I will single out my monthly recipient for Good Heavens. And this month, I think it'll be only apropos to give it to Justin Hawkins, who put in a lot of work, especially today. You can see Justin, he's there. He's the guy with the mustache. He's the only one up there with a mustache. Is that true? Oh, except for Jose, but that's a picture.
I never thought I would make a Good Heavens. Wow.
Yeah, you did. Look at you now. Well, this is what your sweat equity has gotten you. Justin is a brand new board member. We're so happy that he joined us there. He is also our door prize editor. He's the one making sure that you get whatever you get from the store for winning a door prize here. He is a veteran of the Star Party Silver Lake things, and for whatever reason, he always draws the weirdest guests, like historically, and we miss him there dearly because now he's not in LA anymore. So now we always have to deal with the weird people that used to hang out with you. So we're sharing your load. We're spreading it across multiple members.
Say hi to Spaghetti Eddie for me.
Oh, I know. Trust me. He hangs out with me all the time now.
He was on point Thursday.
Yeah, he was. He was in rare form. That's true. Okay, but yes, thank you so much, Justin. The web store, I think, will reflect the taste of more than it has in the past. And if it still hasn't reflected your own taste, mention it. There's a lot of stuff that we can put up there. We're trying to be as inclusive as possible with how you represent the clubs, should you choose to publicly. You can reach out to me, and then I'll put it to Justin at president at laas.org. I'll be his buffer. Thank you very much, Justin. It's awesome. It's a pleasure working with you in all those capacities. Also, there's a little tie-in here. As it turns out, the very first thing I did for the club, I went up to Mount Wilson for a Mount Wilson Star Party that turns out wasn't there because I wasn't officially in the club yet. I was still waiting for my acceptance, and Daryl saw me up there, and he's like, "What are you here for if you're not for the 60-inch?" Because they were doing a 60-inch thing that night. And then he included me to the 60, even though I wasn't officially in the club yet. And as it would happen, Gabriella was there. And then I remember him because that was awesome because I knew about LIGO. And then I was looking at an old picture from that, and then Justin was there too. So it turns out I met Justin on that night also. So all things together. Bless up.
I just remember wondering, when Gabrielle was there, I was just like, who's this smart guy here? Like, he seems to know a lot more than everybody else.
Yeah, I know. He definitely made an impression, that's for sure. I mean, because we're all sitting there talking to him. Meanwhile, like the 60 inches on something amazing, and everyone's just listening to him talk about LIGO. Yeah. He's like, this is old tech. He shrugs. Very confident. I love it. Okay, let's do some door prizes. I think the time has come. Let's give up. We got options. We've got in-house. We've got green lasers.
We have two things here. We're only going to do two things, two of these here, and two of these online.
Online. That's right. So it's going to be 2 per. The hoodie is available to you. Behold. You can choose from this. You can choose the some water bottles that were.
Why don't we do the Vanna White? LAS 100.
Yep. This is these were limited edition from the banquet. We had a couple spares. So that is something you can get. If you want to eschew all of this and get a green laser, that's a thing. If you want to eschew all of it and get a $50 voucher at the web store, which is minty fresh, might be a thing for you, that's also available. But we are ready to start drawing some cards.
And when you're doing that, those of you on Zoom, go ahead.
Yeah, we'll do our 2 first, right? Yep.
Yep.
This is my first draw.
I don't get accused of.
Yeah, I'll take the hit. Okay, so wait, is it the last 3 numbers? All right.
The numbers are 833-5511.
Woo!
Got a winner. Come on down.
Mike, what do you want?
What do you want, Mike?
Yeah, I'm going to take the ghosted jacket.
Literally. Well, you gotta take it off me. That's the thing.
Oh my God. Da 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 da.
This is gonna go full TSA.
They're hugging each other. Oh my God. I'm glad we don't have a camera on this.
Finish it.
Is he wearing something underneath?
I hope so. You're gonna be freezing on the way out, buddy. He wears your shorts anyhow. Okay, next one.
This is the first time I got Michael Jackson.
Is his wallet in there too?
No.
Oh, yeah. Darn.
Remember the cargo shorts? Zing!
The next number is 833 5528. 528.
Yeah.
Who's got that? All right.
I told you.
You're the winner. Come on down. What would you like? It's Riva, right?
Robbie.
Robbie.
Yeah.
Sorry.
I told you that you were gonna draw me, right? So.
Yeah, you're very welcome. I had.
So what do you can pick an item off of Dave.
Oh.
This is how this is going.
No, it says David. You can't have it.
That's across all the names.
No, cross out the name.
Do you guys have any lasers this time?
Yes, yeah, I think we have some up there. I'll go get. Okay, all right.
Okay. Awesome.
Okay, that should do it here.
Okay. We'll take it to the. We'll give it to Zoom. Yeah, it's up top.
Give me just a minute to get the list together.
Nice. Check it out. Pretty good quality. Yeah. No, you should.
Flies too.
Yeah. It's got new. Smells good. Well, how's it taste? Gotta throw it back.
You're gonna want to charge this up.
We're such a weird group.
Okay, we're ready.
Thank God.
All right, ready for the Zoom?
Yep, all you. Show is yours, Spencer.
First one is Tim Thompson.
Oh my God, that's like two in a row. I think he
I have
forfeits.
no idea how that happened, but I did not rig it.
Sure
you didn't.
He's got like $500 worth of store credit up there. He's going to bankrupt us all when he cashes in on it. I'll restate what I said last time we did this, Tim. They don't accrue interest over time by not using them.
Okay. Thank you.
Teresa, what's your cat's name?
All right, ready for the
His
second
name's
one?
Kepler.
Oh, of course. Oh,
Hi, Kepler.
that's so cute. That was the best answer.
Okay, ready for the second one?
Bring it.
David Hasenauer.
Congrats, Dave. All right. Actually, yeah, this is a really good time to win, I think, because there's all kinds of new stuff to pick from. Okay, that's amazing. Let's get into upcoming events, and then we will be officially through the agenda. Our next general meeting here and in Zoom is going to be on April 13th. That's a Monday. The next Griffith Star Party here, not on Zoom, is going to be on March 28th, and it'll be the last one before the super big one that Laura May was talking about. So if you want to get some reps in before the big one, that's it for you. You can start stretching then. Outreach is coming up. We have Silver Lake this Thursday, 3/12. The next big one with the band and everything like that is going to be on 3/26. I don't have information on when the next Santa Monica one is right now, but I'm sure it's going to be happening. Other outreaches include LA Historic Park, also on 3/12, but it's early enough that you can double dip. I think I'm going to do it, and I know Andy's going to do it too. So it's going to be mostly solar. It's not too far away from Silver Lake, so it's actually kind of like, you can be We can go on tour on that day. Not bad? Yeah, and it's part of a flea market? What is it? What's the Baker's Market? Baker's Market. With an N? All right, so it's not financial. It's baked goods. That's awesome. So yeah, maybe do both. And then there's going to be another event in Arcadia on the 27th. I'm excited to announce that I'm not pushing off the. I know when the next family night date is, and it's going to be on April 11th. That's going to be a really, really fun one because we'll be christening the new toilet, which if you haven't been part of this saga, it doesn't seem like a big deal, but I am elated. I am so elated. We keep joking about bringing a bunch of Taco Bell up there to really get our money's worth, but I think I'm going to do it. I think I'm going to do it. Right, though? Okay, next Dark Sky Night is going to be on March the 21st, although it is also that's the weekend for Messier Marathon, so there might be a little trip going on into another spot, so watch out for details about that. There's already sort of rumblings about that, positive rumblings. Mount Wilson Star Parties are not quite on the map yet. Same thing goes for 60 and 100-inch nights, but soon, we're getting to that time of year. If you want to sit on a board meeting, which I mildly recommend. It was actually, the last one was fun. Actually, we had a really good time during the last one. It's really gotten to be a good group of people, and you can see how the jurisprudence of the club works out. It's a Zoom thing. It lasts forever on Wednesday nights. The next one's going to be on April 8th. And then the next Lockwood Committee meeting is going to be the preceding Monday on April the 6th. And this is a fun time to be in the Lockwood Committee right now because there's a budget to work with, and there's a lot of cool plans for what we're going to do in the future there. And that, my friends, is all that's fit to print. So thank you very much for coming. Thank you all of you in Zoom. Thank you again to Gabriella. What a guy.